Okay, looking at some multiple choice questions dealing with applications of derivatives. First question, number 2, is dealing with the second derivative. They give you a table of values and ask which of the following must be true. A and B are dealing with increasing and decreasing, and the best way to determine that in calculus would be to determine if the derivative is positive or, or negative. And there's really no information here that will help me to determine that, so I don't like either one of those. A local maximum, while the second derivative can be used to determine a local maximum, you would also need the first derivative, because in order to have a local extrema, first thing you're going to need to do is establish is f prime of 1 equal to 0. And while f double prime is equal to 0, we are not sure about f prime, so I don't like that one. D is the first really intriguing one. D and E are both dealing with inflection and concavity, which are both second derivative questions. An inflection point, your first thought should be that f prime must change signs. And with that in mind, D is a very tempting option, because at 0, f double prime, I said f prime, this should be f double prime. F double prime is positive. At 2, f double prime is negative. However, we are not 100% certain that the change occurs at 1. And so what I've done over here is I've drawn a function. It is possible to hit, I've plotted these points for the second derivative. It's possible to hit all of the given points without creating a sign change at 1. So I could come down, hit 1, go up, and then come back down, hit this point, and then go back up to this one. It is possible for me to connect to these 4 points that way, and if I do, I have satisfied the conditions. However, the sign change occurs somewhere other than 1. Now, so that one doesn't have to be true. Now, of course, it is probably more convenient to connect these in the most obvious way, and that would be coming straight through and then back up. And in that case, the inflection point could be at 1. However, it doesn't have to be, and we are looking for the one that must be true. So E must be the right answer. And the reason this one is true is because here they're just saying f double prime changes concavity, or f changes concavity. So that means my second derivative changes signs. Somewhere from 0 to 2, and since f double prime of 0 is positive and f double prime of 2 is negative, then there absolutely must be a sign change somewhere between the two. There's no way we're going to connect 5 to 2 to -7 without crossing the x-axis somewhere, and that's really kind of a intermediate value theorem question, but we haven't reviewed our theorems yet. So that one's probably going to be the one that takes the most amount of explanation. Let's see. F is a function given by these. We have a f of 2, f prime of 2, and f double prime of 2. What is the value of the approximation of f of 1.9 using the tangent to the graph? So we know we need a point and a slope. The point is almost always found by plugging the x coordinate, which is 2, into the function. The slope is almost always found by plugging that x coordinate into the derivative. And they were nice enough to explicitly give you both of those pieces of information. The second derivative is not going to come into play on this question. And so my tangent line, y minus 1, is 4x minus 2. And in a linear approximation question, I like to move that y coordinate over. So y equals 4 times x minus 2 plus 1. And then my function's value at 1.9 is going to be approximately whatever you get when you plug 1.9 into the tangent line. So 1.9 minus 2 plus 1. 1.9 minus 2 is negative 0.1. So 4 times that is negative 0.4. Whoops, not 4 point. Negative 0.4 plus 1 is 0.6. And so here we are given the graph of the derivative, and it asks on what interval is f increasing. And so a function increases whenever the derivative f prime of x is positive. We are looking at the derivative. A positive derivative, since I'm looking at the derivative, means this thing needs to be above the x-axis. That happens right here. And there is a 0 at 1. However, the derivative is positive on both sides. And so it's okay to blow straight through that. You do not have to split the interval. And so we are increasing from -2 to 3. That was a quick one. Okay, so this one looks kind of similar. We have the graph of the derivative again. And I didn't stress this on the last question, but do remember that if you are ever given a graph, make sure you pay very close attention to what that graph represents. This graph has horizontal tangent lines at -1, 1, and 3. You probably would have assumed that. However, they very frequently put that in the description just to make it explicitly clear. At which of the following x values does f have a relative minimum? Anytime you see relative minimum, your first thought should be f prime changes from negative. Your function must, oh, that's maximum, not minimum. Relative maximum, the derivative changes from positive, which means your function is increasing, to negative, which means your function is decreasing. Remember, we are looking at the derivative, and so a positive, if you're looking at the derivative, means above the x-axis. Derivative means below. We change from above to below the x-axis right here. And this is really, something happened when they generated this graph because it looks like it's crossing just before 4. However, 4 would be the best answer of the ones given. So here we are looking at the second derivative. Now they gave you this weird representation of the second derivative in terms of a and b. However, the fact that the graph is given means we don't even need to worry about that equation. That's really more of a distractor to see if you can get sucked in to a more algebraic approach for answering this question. They're asking us where f has an inflection point, which is when f double prime changes signs. Does not have to change in one particular way or the other, just from positive to negative or negative to positive. We are looking at the second derivative, and they do tell you that a couple of times. And a sign change means you cross the x-axis. Happens right here at A and at the origin. Okay, so 19 is a tricky one. Is there anything behind my head? Yep. Okay. G is twice differentiable. They tell you that G prime is positive, and that should immediately make you think that G is increasing. And G double prime is positive, which means this G is concave up as well. So we're expecting G to look kind of like e to the x. That is an example of a function that is increasing and concave up. So it better look like this all the time, because it does say for all numbers x. Okay, they give you two values of G and what is a possible value for G of 6. So I didn't plot the axes, or I didn't draw the axes, but I plotted 2 points for G of 4 and G of 5, and we're looking for a reasonable value of G of 6. The first one I would immediately eliminate, first two, are 15 and 8, because if G of 6 were 15, then at 6, it would be somewhere down here. So that'll be the ordered pair 6, 15, and you must decrease from 18 to get to 15. If you wanted to try 18, then you are even with the point at 5. And so 518 to 618, you are constant at least. Now, there could be waviness in between, but if a function is strictly increasing, you cannot have repeated y values. So that's not true. Now, 21, 24, and 27 all satisfy the increasing question. So now we have to focus on what does it mean for something to be concave up. And if you sketched something that was concave up, then that means that as you've increased, the amount of increase increases also. And so I increased 6 units to get from 12 to 18. If a function is concave up, if I increased 6 units again, actually I take that back. If I tried to increase 3 units to get to 21, well, an increase of 3 units would not allow me to be concave up. I'm going to have to kind of level back off and swap to concave down to hit that point. So that one's out. If I tried 624, that is an increase of 6 units. And so if I increase the same amount again, well, increasing 6 units would actually create a linear type situation. And if you are concave up, you cannot have 3 collinear points. So that one's out. And 27 is the only one that makes sense, because to get to 27, you would have to increase another 9 units. And if you increase 9 units, you are increasing the amount of increase. And that does fit the situation. And so 27 is the only possible value for g of 6, given that information. And then the last one is 22. You will definitely need to use a calculator on this one. And there are 2 ways to do this one. And I know, y'all know me, I'm of course going to think graphically. They give you the derivative of a function, and they ask for the x-coordinate of the inflection point. Now, I have told you many times that if you ever see a reference to inflection point, your first thought should be f double prime changes signs. So one way you could do this would be to find the derivative and then see where the derivative changes signs. And that's really not that difficult, because you will have a graphing calculator for this one. And so finding the derivative, just throw it in the calculator, store it into the graph screen. And if you look at f double prime goes from positive to negative right here. And I didn't bother finding the actual x-intercept, because looking at these choices, 4.7 or 0.473 is the only one that makes sense. If E said none of these, then I would need to actually find it, because it could be that it's at 0.491, and that would not be the correct answer. So I can look at the graph and tell that it's going to be 0.473. However, there's an easier way, or I don't know, I guess it's quicker, because that really wasn't that difficult. And you need to know this method, because sometimes they can present the problem that force you, or that really makes this significantly easier. If you are looking for an inflection point and you have the derivative, the other way you could find the inflection point is that your derivative has a local extrema. So if you're looking at the derivative and the derivative has a max or a min, that is going to be the location of an inflection point. And so I'm looking up here, and I can't tell exactly where it happens, but I can tell that this derivative has a local max somewhere around 0.5. And again, 0.473 is the closest of all of the options they gave you. The reason for that second reason, remember that f double prime is the derivative of f prime, which means f double prime is the slope of f prime. And if you need f double prime to change signs, then you need the slope of f prime to change signs. It's the same thing as f double prime. And so if the slope changes signs, if you change from a positive slope to a negative slope, or vice versa, that will create an inflection point for your function. Those are all of the questions. Hopefully those made sense.